we are seeing one of the fastest tech shifts, I think, in software history. AI is just churning out code.
Massive amounts.
Yeah.
And developers are pushing it into production so fast.
It's boosting productivity, no doubt, but you talk to anyone in security and they're all asking, are we just shipping vulnerabilities faster too?
It's a valid concern. And honestly, for a while, we didn't really have good ways to measure that risk properly, realistically.
So what's changed?
Well, that brings us to this new evaluation framework, A.S.E. That's AI Code Generation Security Evaluation. That's what we're digging into today.
Hey, A.S.E.
Yeah, the mission here is to pull out the key insights from this research. It's designed to test how secure LLM-generated code really is, specifically in fixing critical flaws within a realistic setup.
And realism seems to be the key word. Because we've seen benchmarks before, right? Ones that check if AI can write a function or pass a test.
Right, functional correctness.
Yeah.
But that often misses the security angle entirely. It doesn't tell you about the practical risk.
So A.S.E. is meant to be that reality check, moving beyond simple code snippets.
That's the goal. Look at the older security benchmarks. They often had these, fundamental flaws.
Like what?
They felt artificial, maybe human-written, isolated code bits. Or they relied on evaluation methods that weren't super reliable, like asking another AI to judge security, or time-consuming manual checks.
Right. If the test isn't like a real project with all its messy interconnections, the results don't mean much for actual developers.
Not for building real software now.
Okay, so let's break down how A.S.E. tackles this. You said it has 3 core features for realism, starting with the data source.
Yes, the data source. They didn't just make stuff up. They went to GitHub, found quality open source projects.
Okay.
Projects with known, documented security issues, CVEs, common vulnerabilities, and exposures.
So using actual documented failures.
Correct. They extracted the code related to the vulnerability right from the patches that fixed those CVEs. So every test is based on something that genuinely broke in the real world.
That makes sense. You're asking the AI to fix a bug that actually caused problems. What's the second feature? The task setting.
This is about mimicking how a developer might actually use an AI assistant.
How so?
It's not just about fixing one line in isolation. The AI gets context sometimes, code from other files in the repository, things that influence the fix.
Okay, so cross-file awareness.
Yes. And then it's asked to generate the fix, often in that diff or patch format developers use with Git or other version control.
So it has to understand the project structure, not just the syntax of one file.
It forces that broader understanding, which leads to the third piece, code assessment, how they actually check the AI's work.
And the source material really stresses using customized static analysis tools here. Why not just standard security scanners?
Good question. Standard SaaS tools, the ones readily available, often didn't quite catch the specific ways AI might fail, especially when generating fixes.
AI code fails differently.
Sometimes, yeah, the structure can be unusual. So to get accurate and repeatable results, the A.S.E. team had to tailor tools like CodeQL and Journ to specifically look for the original CVE in each test case.
Hold on, they had to build custom detectors for each vulnerability type they tested just to be sure the evaluation was right.
It sounds like a lot, but it was crucial. Otherwise, you might think the AI fixed the flaw, when really it just created some other subtle issue that a generic scanner would miss.
So it's a serious commitment to accuracy.
It had to be done. Now, looking at the scope, they set up 120 of these repository-level tests. And importantly, 80 were mutated.
Mutated, meaning?
They changed things like variable names, code structure, things to stop the AIs from just succeeding based on having seen that exact code snippet during training, mitigating data leakage.
Smart. And the focus was mainly web technologies.
Primarily web, yeah. 5 languages covered: PHP, Python, Go, JavaScript, Java. PHP was actually half the data set, 50%.
And the vulnerability types.
They focused on 4 really common and damaging ones: SQL injection, that's CWE89, and command injection, CWE78.
The injection flaws. Classic.
Then path traversal, CWE22, which deals with file system access issues. And finally, cross-site scripting, XSS, which is CWE79.
Okay, so hitting major web security weak points, that seems comprehensive. Let's talk metrics. How did they score these models?
It's multidimensional, but there's a clear priority.
Which is?
Security. That gets the biggest weight, 0.6. It measures if the AI's code actually reduces the detected vulnerabilities.
Makes sense. What else?
Second, it's quality, weighted at 0.3. Basically, does the generated code integrate properly? Does it pass basic syntax checks? Because a secure fix that breaks the build is useless.
Sure.
And lastly, stability, just zero point 0.1 weight. This checks if the model gives consistent answers if you ask it the same thing multiple times.
Okay, security, quality, stability. So they ran 26 different models through this. What was the big picture takeaway?
Well, it's a bit sobering. There's a really significant gap. LLMs are still struggling quite a bit with secure coding.
How badly?
Their security performance is way behind their ability to just generate working code. And get this, not one single model scored above 50 points on that main code security metric.
Not 1 out of 26. Wow. So even the best model.
The top overall performer was Claude 3.7 Sonnet. Its overall score was 63.01, which sounds okay,
But
but its code security score was still below 47. So even the best model is basically getting security wrong more often than it gets it right in these realistic scenarios.
and that realism, the repository level complexity, seems key here.
It absolutely is. The research highlights this big performance drop. Models that did well on simpler snippet-level tests, they mentioned GPT-3 on Safe Gembench as an example, really tanked on A.S.E.
Because fixing one line is one thing, but fixing it correctly within a whole complex project.
Exactly. That context makes all the difference.
The results also showed some surprising things about how these models work or don't work, like the slow thinking versus fast thinking idea.
Right. You'd instinctively think that giving a model more time or steps to think, deliberate more, would lead to better security.
More compute should equal better results, usually.
But A.S.E. found the opposite. Those slow-thinking setups, the ones with multi-step reflection, actually did worse on code security than the simpler, direct, fast-thinking ones.
That's really counterintuitive. Any theories why giving it more budget doesn't help security? Maybe it introduces other errors?
The paper doesn't give a definitive why, but the result is clear. Just adding more processing steps doesn't seem to improve the model's fundamental grasp of security principles or complex data flow.
Interesting. But architecture did matter.
Yes, they found that mixture of experts models, MOE models, generally did better on security compared to the standard dense models.
Okay, so MOE architecture seems beneficial. Another finding that jumped out at me was about consistency. High stability didn't mean good code.
Yeah, this is a really important point. You might have a model that's incredibly consistent.
Like GPT-03, it had almost 99% stability.
An amazing 98.91 stability score. It gave the same output nearly every time. But
The output was bad.
terribly insecure and low quality. It scored only 0.36 on both code security and code quality.
So it's just consistently generating insecure code? That's not ideal.
It's quite worrying. Consistency is not correctness. It just means it fails the same way every time.
Okay, let's look at the specific failure points. Which type of vulnerability tripped up the models the most? You mentioned 4 types.
I might have guessed SQL injection myself, given how tricky queries can be.
Me too. Was it?
No, surprisingly, it was path traversal, CWE22. That gave even the best models the most trouble. Scores were below 50 across the board for that one.
Why is path traversal so hard for them?
It seems to be about reasoning around file system interactions. Secure path handling often depends on subtle context, maybe from other files, about where user input comes from and how it's cleaned up or canonicalized. It needs real environmental awareness.
Deep context again. And what about SQL injection? The case study there showed a common failure pattern, right? The qualified but insecure code.
Yes, exactly. Models would generate code that functionally worked it past the basic checks, the quality metric, but it was still insecure.
How so?
Like dealing with user input in a SQL-like clause,
Mm-hmm.
the model might correctly use string concatenation to make the query run, but completely forget to use parameterized queries.
Leaving it wide open to injection.
Right. It prioritizes making the code look syntactically right over making it fundamentally safe. It sees the pattern needed and fills it in without the security guarantee.
And there was one more failure mode related to the complexity, about getting the patch wrong.
Yes, sometimes a model might generate code that was conceptually secure, but the diff it outputted was just wrong. It tried to apply the fix in the wrong place in the file.
So it knew what to do, but not where to do it within the file structure.
Another layer of failure. Conceptual, structural, and sometimes positional.
So bringing it all together, what's the main takeaway from A.S.E?
The bottom line is, LLMs are getting pretty good at generating code that works, functionally speaking. That's why those quality scores are often decent.
Right.
But they consistently fall short on security, especially when you put them in these realistic, context-heavy repository-level situations. The security understanding just isn't there yet.
It really highlights that practical software development needs more than just working code. The source material frames it as needing three things at once.
That's right. Secure coding practices, semantic correctness, making sure it works functionally, and structural applicability, meaning getting the patch in the right place.
And just hitting one or two of those isn't good enough.
Not for real-world software. And the fact that even top models are scoring below 50 on security shows just how hard it is to get all three right simultaneously. Relying on AI for critical security fixes without significant human review looks pretty risky right now.
It really drives home that gap between just making code run and making it genuinely safe, which leaves us, and you listening, with a crucial question as these tools become more integrated. How much can you trust the output, especially when this research shows they struggle most with the hardest, highest stakes security problems? That's something to keep in mind.